Welcome to day 2. It is Helen who is going to start with a recap of kinting. I know people must have wondered what is kinting. So he's going to make sure that you understand how to kint in R while using Markdown. I realize that if you learn R Markdown, you're able to write your thesis very fast. As you analyze, actually, you write. So pay attention, and then afterwards, we'll go into hypothesis testing. Thank you. I hand over to Dr. Helen.
Thank you, Professor Susan. A very good morning to everyone. I want to confirm if you can hear me, then I proceed. Can you hear me? Just type a yes in the chat. Great, thank you. Welcome to day 2. I'm just going to give a recap on what we looked at yesterday, especially when it comes to the R Markdown. And like I explained yesterday, that an R Markdown, it's like a notebook. So it supports you in the writing. Even you can, like Professor Susan has said, you can write your publication using an R Markdown, whereby you run a code and then automatically the results come along, such that everything is in one place. But however, to run our R Markdown, you need to first have the R script. That's when it will be very easy for you, such that everything is put together. However, yesterday I left an assignment before I proceed, and I'm just wondering if there are people who try to do the assignment. I told you to convert the follow-up one script into an R Markdown. So in case there's somebody who tried, we can get 2 people to share with us, and then I see what you have learned, and I'll supplement from there. Anyone willing to show what you did, you can raise your hand, or you can write the name in the chat. Anyone willing to participate, to show what you did, and then such that you're muted? There is one saying yes, Fano Sekebebe, but it's an email. Maybe send me your name, write your name, such that it becomes easy. I want 2 people to share with us what you did. Share your name. If in case you want to show the R Markdown that you developed from Eshetu. Eshetu is willing to show his R Markdown from yesterday's work that we had. I kindly ask David, like you allow her to share with us what she has. Even Samuel is interested. Yeah, we need only 2 people, so Samuel will present, and then Eshetu as well. David, please, can you give permission to Eshetu to present his R Markdown, and we have a look at it if he did the right thing. David, are you there?
Yes.
Yes, we have, Dr. Runyara, we have 2 participants that we want to share their work. So give rise to Eshetu to be the first person, and then someone will be the next.
Eshetu can talk, but
can unmute.
Can unmute and talk.
What about sharing? Because it's in R, so we need to see what.
Okay, David is working on it. The second person is who?
Samuel Okrut.
Okay.
So can we get started? You've given them the rights?
Yes, we have given them the rights.
Okay. Eshwati, please, can you share? And I see what you tried out. We're going to have 2 people only, and then we proceed. We want to hear from you. Take us through the procedures.
Okrut is already is now a panelist now, so he can present. Samuel Okrut.
Okay.
Yes.
Samuel. Mm.
Hello, good morning.
Good morning.
I don't know whether this is what you meant, doing the follow one up in,
Yes.
in R Markdown, and this is what I did. So
Take us from the beginning, scroll up. Okay. You can explain, just take us through what you did.
so I opened an R Markdown document. Then this disturbed me a bit because I had to change the directorate. I had saved it in a different, I transferred the folders in a different file, so I had to change the directorate. And I just Googled this, and this is how I got that. And then I copied and pasted what was in follow up one, and then I put this in a chunk and run. Then set my new work directorate, which is this. Then imported data. After importing data, I went and did all the steps as the way in the follow up one. So this is basically every step, but every chunk has a peculiar a function that I have to run. So for example, when you look at summary, I put it in a chunk, I put the notes up, then put every other function that I have to run in a chunk. And that is what I did.
Did you try to run it? Can you run and we see what you get?
I ran them, that's why they appear here. I don't know if I can rerun.
Kint and we see.
This is when that's what comes up. And when I run this, it's also this goes direct to the global environment. And if I check it up, and this is how it looks like. Yeah, so basically I did
first get back to our Markdown.
Pardon?
I want you to kint to an HTML to see if the whole document is okay. Did you get that?
Yes, but now I have an issue with the last bit, which is this. After I run this,
first comment that.
After I run this becomes high and low. But when I run the second one, this brings this error.
First time. Now, what you can do first comment that. Put a hash at the beginning, because what you're trying to do is that as you're running a document, you can even be able to check the errors when you're able to correct the errors in every chunk that you're having. So first comment on that, and then we proceed. I'll comment in general. Put a hash at the beginning of cross. Put a hash. Then also come to the downer one and put a hash. Kindly, the rest, ensure that you pay attention, okay? Was there any other error in that, or that was the only one?
That was the only error.
Okay, now let's kint. Now, a second, before you, since we've commented on cross, then it implies that you're going to get an error also in this other part. Can you delete what you have down here to know whether the type of colors made a difference? Just delete off that part, because it's still going to bring a complaint. To know whether the type of colors, delete everything, even that chunk, yes. Okay, great. Now let's stop there for a meantime. And then just to alert the other colleagues what someone has presented or what someone is still presenting, we want to see that we put all what we have in our script. She got what was all in the R script and then pasted it in our Markdown. Then on top of that, there were notes, okay, because we had notes within within the R script. So you can even put notes within our Markdown, such that you're guided very well and you're able to refer back to what you did. And the other thing that you have to note in mind, that every code, okay, he put it in a chunk, okay? Everything that you need to run or that need to produce a result within the R script has to be put in a chunk. And at the same time, you can also be able to run a particular chunk. You don't need to run everything. And that one is very important in the sense that maybe you want to track some errors, okay? In case there is an error, you need, then that one will support you to check which chunk has an error. However, when everything is okay, then you can run, you can kint and get a document. So Samuel, can you kint and receive an HTML? Okay, there is an error. It is saying that error, line 24. Okay, run again. When you're running, you have to look in your console. There is what we have an R Markdown.
Okay. Error in line 24.
Yeah, go to line 24 and comment learner R. Comment on it.
Line 24.
Continue upwards. No, it's a library. Continue. Yes. You come and put a comment on learner R.
Learner R.
Yes. Okay, comment on that. Just put a slash. Try to kint again. Kint or create to HTML again and we see.
Yeah, I'm doing that.
Okay. So we are seeing in the down here, there is a process that is going on, and it starts building the different percentages. The moment it gets to 100, you'll come up with the results to show that it's correct. If there is an error, it will still tell you that there is an error somewhere. Okay, we can see that now what Samuel has done, he has been able to get an R Markdown whereby all the libraries are there. He has got the codes plus the results. So you can use this as a notebook. You write your notes or a paper or even your thesis such that you're able to put everything together. So Samuel, thank you so much. If you want, you can go, that is an HTML. I wanted you to kint to PDF and then Word, but you've stopped sharing.
Oh, okay. Sharing again.
Okay. Now that is an HTML. Cross that. You can cancel. You can find this document in the folder that's having all the work that you set as your working directory. That's where you'll find it. You can close it and then kint to PDF and we see.
That's what I'm doing.
Kint to Word. Just hold on. It is already running in the background, so I think you need to key to Word and receive. Go back and key to Word. Now, what this comment is saying, that no LaTeX installment detected. You find that if you're running, if you're running, sometimes within our Markdown, it has got LaTeX in it. Those of you who are running some mathematical formulas, LaTeX is a software that you can use. So LaTeX is embedded within our Markdown. So as you're running the PDF, then you have to have LaTeX installed on your computer such that you can get the PDF output. Yes, so that is the word part. So in case you can't key to any output that you want, and then later you take the results where you want them to be. So that is how the word output looks like. Thank you so much. That has been great, and it shows that people are understanding what we are doing. There's a question in the chat. How do I run the R Markdown? Where do I click? Okay, Samuel, thank you. Can we hear from Eshetu? Are you ready?
Eshetu's network is unstable, so probably we can even, yes, we can have another person maybe who's willing, so
okay, any other person willing? Just one person to go. Anyone willing to share what you did yesterday as an exercise, converting the R script into an R Markdown? If you want to share, just write your name in the chat, or you can use the raise hand icon. Okay. It seems that it's only Samuel who did the exercise. What about the rest?
We are trying to promote Muisa Msongora.
Dr. Onyaro, you're saying that somebody else is going to present?
Yes, we had promoted some participants. Muisa Msongora.
Okay. Muisa, kindly share and we see what you did. They are Markdown. Okay.
You need to unmute Muisa.
Yes. This is just what I did.
Please take us through.
Okay, I was just, I also tried just to open my R Markdown, and I started by renaming it as the title, the author, and so on. And for me to just open every, okay, I was also trying to make sure that to open a chunk, to have every code or every command in the chunk, and to get a new chunk, for me, I used to get it by clicking on Ctrl, Control, Alt, I at the same time simultaneously, and I was getting the chunk. Just Control, Alt, and I was just helping me to get the chunk, and then I was able to copy.
Kindly say it again. It's what?
Control, Alt, and I.
Okay.
Simultaneously. So I was able to get the chunk, and I could easily copy my commands from my script to the chunk.
Okay.
And that's how I proceeded with all the codes that I had. But unfortunately, there was one of the libraries that was giving me a hard time.
Did you delete it? I think that was Lana R. You removed it?
Yeah, I removed it. Yeah, Learn NR. I removed it and it worked.
Okay, great. Can you key for us just any style, HTML or Word, and we see? As you're kinting, you have to give your computer some few minutes, and then it will be showing you that because it has to go through every chunk, that we are chunk 1, so far it is 6%, and then keeps on moving until it gets to 100%. The moment it gets to 100, then that's when you'll be able to see the output.
Okay.
Yes.
But
because it has to.
Unfortunately, I was facing a challenge. It seems that for every code that I had to run inside the chunk, I had to put the library inside every chunk and not having run just the libraries in the first my first chunk.
Usually, it is always good like that. You put the libraries in the first chunk, such that they are run once, and then it's very easy for you to get the output.
Okay.
Yeah, because as you're saying in the R script, still we start with the libraries. Then after libraries, what we do, we move on to importing data, setting the working directory, then importing data, and then we proceed with the analysis.
Okay.
Have you got the output? I'm saying it's already 100%, but we're not seeing it.
Okay.
Maybe you can check in the folder.
I have the output already.
You have the output already?
Yeah.
Okay, fine. Thank you so much for sharing. Thank you, Samuel. It has been great. So far, we've gotten 2 people that did the R Markdown, which that is so good. Let me ask in the chat, can I do a recap of R Markdown just in 5 minutes, or it's okay to everyone? Just in the chat. Okay. For the different participants that try to do the R Markdown, thanks for the great work done. That is so good, because as you keep practicing, then you learn a lot of things. So it's always good that in case we give you exercises, kindly work through them, and in case there is an error, you can able to ask us or try to Google on internet and see where could that problem be. Like I said yesterday, an R Markdown, it's like a notebook, okay? Like we did in the R script, where we are putting the comments within the R script. This time around, within the R Markdown, those comments can be your notes, such that you are able to read everything step by step. You can create titles in the R Markdown, like as if you're writing a manuscript. So that is why we are having R. And within the R Markdown, you can have it in different saving styles. You can either save it as an HTML, like what we saw in kinting to HTML, or it can be a PDF, or you can kint it to Word, depending on what exactly that you want. And when you run an R Markdown, what happens is that the important thing is that we create chunks, or call them blocks. And within these particular blocks, it's where we put our commands. And you can run every chunk one at a go, such that you're able to track in case there is an error. Because as you're running, it will still tell you there is an error on line 25. There is an error on line 3, such that you can quickly work through it. But in case there is no error, automatically when you kint, you'll be able to get the results. Okay, now let's proceed. How do we get to the R Markdown? Within R, okay, we are going to see, you go to File, then New File, you click R Markdown, and then it's going to bring you a certain screen. There are 2 options that we are going to see, okay? And then on that particular screen, you can put an author if it's you that are writing out the R Markdown. and then you save it also a different name. And then what is important again, you need to create chunks within the R Markdown, because all the codes have to be put in a chunk. You can have as many chunks as you can have 3, you can have, I mean, depending on the length of your R script that you're transferring. And I said that if you go to R, we are going to do it again. You go to File, then New File. Now on the new file, you go to R Markdown. On the R Markdown, you're going to come up with, you're going to see this interface that I'm showing you. And they will ask you to label your R Markdown, the title that you want to give it. Maybe it's a thesis, and then you write the title of your thesis there, because it will appear on top of the script. And the default outputs that are given within R, we have the HTML, the PDF, and then the Word, like how our colleagues have showed us. And then if you don't use the previous option of file, new file, and then R Markdown, you can come here, the second option, where you're seeing this icon, you click on the drop down, and then in the drop down, you'll be able to read out the R Markdown, and then you click on it. All right, when you click on it, then you'll be able to see the R Markdown. Now let's move on to R and we get more details. I kindly ask you to also try such that we do these things together. Okay. Like I said yesterday, R Markdown has got a template that is being given to you, a template that you can use, all right? So what you need to do, let's start step by step. You go to File, New File, and then as you walk through the new file, see what I'm doing. There's what, then you move down from R script, R notebook to R Markdown, okay? Then you can click on it. That is option 1. The other option could be you just come on this icon, you click on it, and then you'll move direct to R Markdown. Those are the steps that you can take. When you click on it, it's going to show you the new R script. What title do you want to give it? For example, you can say any title that you want to give it. I can. Yesterday I used my first R script, so you can give it maybe proportional tests. That is the title that I want, but it varies depending on what you want to do. And so after that, you scroll down and then you click OK. Okay, that is the first procedure. Now, the moment you click OK, this is what you're going to see as your script in the R Studio. Okay, within the R Markdown, you don't need any code. All what you're doing, you're transferring the R script into an R Markdown such that you're always able, it is easy for you to refer to it and you don't need to run the codes again. Now, first it has given me the title that I proposed from the previous slide. Then the author, it will always indicate your name, and then the date, and then the output. By default, like we saw earlier, it is HTML, but you can convert it to a PDF or a Word. So now looking at this, yes, I need the upper part. I'm going to leave it there. I also need to create chunks. I'll leave the first one. But now what I can do, I can come to the R Markdown from here where I put the cursor. I delete everything because that is not part of my work. When I delete everything, all I need to do, go back to our script, in this case, which is the follow-up one, and copy whatever that you need from there. So what I'm going to do, I'm just going to copy a few things. I'm going to come and copy my libraries. Okay, I'll copy, for example, I'll stop there. Just a demonstration, but you can do it on all your script. So what I do, I bring it, I paste everything now in the R Markdown. All that I did in the R script, I copy it, I paste it in the R Markdown. The next thing that I do, I start creating chunks, okay? And so I go back to the start, and what I do, because I need procedures, remember I copied all the things from my R Markdown. So what I can do, because these were commands, I start creating the first chunk, that is R, and then I have to close it. My first one, I say that it's only going to have my libraries. If you want to create titles, it is also possible. Usually you can put / and then setting working directory. That one works as your title. And then I can put everything still under, I can put everything in a chunk. But where there are comments within a chunk, they will still just come up as words. Nothing is going to change. So I create another chunk. I open, I put R, number 2. Then I can say that, of course, this is, I can comment on that. I only need to set my working directory, and that is the command that I have. Then what I do, I can close that and I select that chunk, stop there. It doesn't matter what length that you want. It's up to you, because by the end of the day, what you need is the output. Then I say I want to have another title, data frame, and importing data, just like to guide you, you're able to recall everything. So I create another chunk, I call it R. Then I can come and say, let it stop there. Whereby in here, I'm importing my data set, and then I want to see the results of a string. I move down, I can create another chunk, R, and then I decide where I want it to stop, depending on what exactly that you're doing. I can say, let it stop there, because what it's going to do, it's going to run a code and gives me the output. In case I don't want the titles or the wordings, I can put everything in a chunk, okay? Such that still the moment it runs, those words will come automatically. I can say, okay, let that chunk stops there. What guides you, it is you to decide. There's no criteria that you're going to use. And I can say, okay, let the rest of the material, I'm going to run everything, and I close it in just that chunk there. Somebody was asking, how do you print? So it is always important that you save your document. When you look here, this document is not saved, it's untitled 1. So you can save it by clicking here on Save Current File. The moment you save, it will take you where you want to save that particular for the R Markdown. So I can say, I want to save it in the follow-up B1 materials, okay? For example, I can still call up follow-up. I can call it follow-up 1, such that I'm able to remember that my follow-up 1 R script, I created an R Markdown for it, and it becomes very easy for me to understand that this script, I've already created an R Markdown for it, such that I move on in a more organized way. So I'll save. And when you look here, now you've changed the title to follow-up 1 R Markdown. And then when you're done with that, in case you're interested, what you can do, you can run each chunk at a go. For example, you can say, here I've got a chunk of libraries. I can come and just run the first one, okay? Hope you're seeing you come to this pointer, run current chunk. So you click, it will only run in that particular section. Sometimes it's important to run each, such that you are able to track where the error is, other than running everything at a go. Okay, now you move on, you come to this one, you can also run it, and then it will show you that the moment it is successful, you will not see any error in the R console. You can also come to this one. There's something I want to show, because I need an output here. So I can come and run. So because str diamond will give me an output, so it is going to come down here. The moment I run, it will show me that this is the output, okay? Under the str diamond, that is a structure, it will give me an output and tells me that, okay, it's a data frame with 100 observations and 7 variables, plus the other variables that are embedded there, and so on. I'm just doing this just for a demonstration. So you can keep running all the chunks separately for you to be able to track in case there is a problem. Where do you start from? Because sometimes you can run and you get errors, but then those errors can easily be tracked, and then you get the right thing. So I can run the last one that was for each. And so after that, when in case all the chunks have run successfully and I don't have any problem, all I need to do, I can now kint, or you can kint at a go. Like in kinting, you want either to create an HTML or a PDF or Word. So most of the time the default is HTML. You come and click on it, but you have to come and look down here because it will tell you that the process is going on. Still, it is showing me that, move to line 13, there is an error. So all you need to do is read the error and go back and see where the problem is. So with that, I need to move back where there is an error. And then most of the time, the first thing that you can do, first comment on that error and run to see if it's coming out, if the results are getting up. If they are not, then you have to go back again and run the chunk and try to see. In case I comment that, okay, because it's an error it is complaining about, I try to kint again and I say, am I going to get the results now or it's not going to? You wait for it for a while, and then the moment it is ready, you will see the output automatically. So my output now, I've kinted to an HTML, or I've converted to an HTML, my R script, and these are the results. This is what it's giving me. Remember the title that you put, who is the author, you yourself, and then it also tells you the date, and it shows you the libraries that you used. Remember, this is the title. I said you can set titles, you can write notes within an R Markdown. It all depends. It is like a notebook, it's guiding you. Because even like after 2 days or after a week, you are able to go back and check, okay, why did I do this? Because they are notes attached. You can quickly follow through what you're doing and then also reproduce it on the next work that you have. So this is what we have, what it's doing on each code that you run. The one that needs the results will come automatically. Like here, we said you want summary of diamond and price. So on the next line, it will show you that this is the summary, okay? And then you'll move down. Here, we wanted to get a table for diamond and color. The next part, the code, and then the output. It gives you the code and then the output that you expect. I'm going to stop here and pause in the chat and ask if you've gotten the concept, but you can also try it now and see what happens. Okay, I'm just in the chat. Is it okay now? Hmm? I need to check it again. Okay, given that the big percentage is saying that it's good now, go ahead. Could you please open the output file? Yes, show us the HTML. The HTML is the one that I was showing. This is the HTML. Okay, somebody is saying that, can I show you the HTML? A second. The HTML that I'm getting. This is how it looks like. This is the HTML, how it looks like. The moment you run R, this is the output that you're going to get. The HTML that I was talking about, whereby it shows you your codes and then the output that you get. So this one, you can keep it as a file and you can always refer to it. Or you can use it as you're writing your different work, because it keeps the record of the notes, or you're writing notes somewhere, and then you're able also to embed your codes automatically, and you get that. In case you don't get an HTML, you can convert it to PDF, or you can convert it to Word, like how our the different participants have shown. So is that okay? I'll share with us the slides. I will do that. Okay, can we proceed? Try to do it. I'm giving you 2 minutes. Try to see if you can convert your work now into an HTML. Just get a few lines that you can try on. Get a few lines. Try to get an R Markdown. Maybe at least the first, for example, 10 lines. The moment it converts, then automatically that is the same procedure that you're going to use on the rest of the other codes. I'm giving you 2 minutes so that you try to see if you can convert the follow-up. Just pick a part of it, convert it into an R Markdown. And then I'll ask in the chat again, okay? Yosef is saying that done, that is good. I want to see more dones. In case you've got it, type in the chat that done. Okay, so far there are 3 people. Okay, that is great. I think that is a good recap with the exercise that we sent, and most of the participants are saying now they have gotten the concept on how they can convert the R Markdown into R. Kindly comment the learner R in case it is giving you an error such that you try to run it again. Comment it in the R Markdown, okay? And sometimes when you're getting that particular error, most of the time it implies that the same package is also embedded in a different package that you have up. For example, like the tide verse. So when you comment on it and try to run it again, then automatically you see that you're able to get the output. Okay, great. I'm going to stop here, and then Professor Susan continues from where I've stopped. So can we proceed? Okay, at least now, yes, great. Okay, there's a question in the chat that what do I recommend between R, dealing with R and then R Markdown? You need both. First of all, you have to first have the R script. After getting the R script, then you can run it in the R Markdown. However, as you move on and you master the content, you can also run everything in the R Markdown. But sometimes, because you're not so certain that your codes might work out very well. So that's why I'm recommending that you start with the R Studio, you put your commands, then execute them into the R console. The moment you're successful that you put everything together, then I would encourage you that now shift to the R Markdown, such that everything works perfectly well and you're able to eliminate errors, which you might not do when you work direct in the R Markdown. Okay, that was great, great recap. I'm now handing over to Professor Susan to continue from where I've stopped. Thank you.
Thank you, Helen. I just think that everybody received day 2 notes. And let's continue with the hypothesis testing. I'm going to share the PowerPoint Ndeka mbadde njogera n'omwana n'ankwasa ennaku. Okay, so can you see my everything?
Yes, I can.
Okay, let me now start. Okay, dear participants, today we are now going to hypothesis testing. And from hypothesis testing, tomorrow we'll look at analysis of variance. Then, if all goes well, we will go into regression. And regression, you know, it's a big topic also. So that's how we'll be moving. So for now, let's look at the simplest of simple things, hypothesis testing. Okay. Okay. So under hypothesis, we find that we have two hypotheses in research. These hypotheses can be statistical hypotheses when you formulate them with Greek letters, parameters mu, naught, and mu or sigma. For example, H naught, which is the null hypothesis, is equal to mu naught. That is a statistical hypothesis, or you can formulate a research hypothesis. Hypotheses are two. We have the null hypothesis, which is denoted as H naught, and we assume this is correct. When we collect our data, we assume the null is true. And the alternative is denoted as either HA, others denote it as H1, and it is the assertion that is contrary to H1. So if we assume that the population mean is equal to mu naught, then the alternative would be that the population mean is not equal to mu naught. So possible conclusions from hypothesis testing reject the null hypothesis or fail to reject the null hypothesis. We do not say accept the null hypothesis. So if we fail to reject the null, don't say I accept the null hypothesis. You can only reject it or fail to reject it. So the alternative hypothesis can either be one-sided with either less than or greater than, or it can be two-sided with a not equal sign. Now, an alternative hypothesis is one-sided, maybe less than or greater than, if you know the direction of your research. For example, you've already reviewed literature, and you know that water quality decreases as more sulfur products or nitrogen products are added. Somebody is saying you can't hear me. We can hardly hear you. Okay, I'm going to get closer. Okay, can you hear me now? Okay, thank you. Sorry about that. Okay, I can do a simple recap. I said we have two hypotheses. We have the null and alternative hypothesis. And the null, we assume it is true when we collect data. The alternative is the one which is contrary to the null. For example, if we say that the null hypothesis is that the mean of the population where you're conducting your research is equal to mu, then the alternative will be that the mean of the population is not equal to mu or mu naught. Okay, so I was talking about the possible conclusions from hypothesis testing. We either reject the null hypothesis or fail to reject the null hypothesis. But if you fail to reject the null, do not conclude and say, I accept the null. So we either reject the null or fail to reject the null, depending on the value of the probability from your data. Now, the alternative hypothesis can either be one-sided or two-sided. I was saying that one-sided can either be less than or greater than. You use two-sided if you do not know anything about that research. For example, you're not sure whether the population of that particular site where you're working in is increasing or decreasing. So then you use the two-sided alternative hypothesis. We only use one-sided alternative hypothesis if we are sure from literature that, for example, the water quality decreases with more effluent that goes into the river. And if you're working on water quality, then you can say that water quality as your null hypothesis, your alternative, water quality decreases with increase in nitrogen components. If you're not sure, then you say water quality does not differ with addition of nitrogen products. So that is all about the hypothesis. I also mentioned that there is a statistical hypothesis. Some people say that when you say there is no difference in the water quality, that sounds more of hypothesis than research, but it depends on the journal where you are publishing your paper. Okay, so the hypothesis comes from your objectives, and the objectives come from your problem. So sometimes you find that a student writes a proposal, a nice proposal, without a problem, but has objectives. It happens so frequently. So if you have objectives, and those are the objectives you want to look at, then go back to your problem and make sure that every objective has a statement in the problem statement. Then afterwards, you can now formulate your hypothesis, or if it is a study where you can't test the hypothesis, then you formulate your research questions. So that's just a recap of what we did in our first online lecture. Now, when we are doing hypothesis testing, normally we have two types of error that we have to consider. We have type 1 error, which is rejection of the null hypothesis when the null hypothesis is true. And then type 2 error, rejection of the null hypothesis when the null is not correct. The type 1 error has a probability alpha, and it is normally called the significance level. This probability, we set it as researchers, and in the environment, agriculture, forestry, normally we use a significance level of 5%. But in other fields that are sensitive and dealing with life, the significance level is so small. For example, in medicine, veterinary medicine, human medicine and veterinary medicine, we find that the significance level can be 0.000 something, depending on the sensitivity of the problem. Now, beta is the probability of making a type 2 error. Okay? Now, why do we talk about these errors? It is very important to know that when you commit a type 1 error, for example, let's give an example. Assuming that a lawyer is investigating a certain man who beat up a wife and the wife died. That is the story which is around. Like we are assuming that is a story which is going around. This man is assumed to have beaten his wife and the wife died. So the null hypothesis is that the man is not guilty. The alternative is that the man is guilty. Now, if you commit a type 1 error, means that you reject H0 when H0 is true. Meaning that this man, if it's true that he didn't kill the wife, he's going to serve a sentence when he's not guilty. So that is the problem with type 1 error. And type 2 error, You do not reject the null hypothesis when the null is not correct, meaning that the man is going to be set free, yet he's a serial killer. You'd see? So all these type 1 and type 2 error you have to put into consideration when you're designing your studies. So then how do we avoid the two types of error? So type 2 error and type 1 error can be reduced. So if we increase our sample size, that means that the probability of rejecting the null when the null is true is going to reduce. So when you have a lot of information, whatever conclusions you're going to make are based on sound knowledge. But for example, if you have 10 observations and then you make conclusions, you reject the null, yet the null is correct, then you're likely to commit a type 1 error, whereby you are committing somebody to be guilty when in reality they are not guilty. So then how do we reduce type 1 error? So when we increase our sample size, we are reducing type 2 error. When we use a small significance level, then we are reducing type 1 error, because type 1 error is alpha, is equal to alpha, which is our significance level. So for example, if we set a significance level of 0.01, that means that when you reject H naught is truly correct, that H naught should be rejected. And that goes hand in hand with a reasonable sample size. So we have various formulas of calculating the sample size, which we did in the last session. So you can always refer to the last session to know how to calculate the sample size, and you can put in the significance level you require for that particular research and calculate an appropriate sample size. And then when you come to analyze data, you will reduce type 1 error and type 2 error. Okay? So some people say that if you have a high power of the test, then the type 2 error also reduces. Now, power is equal to 1 minus type 2 error. So type 2 error, we said it is beta, the probability of making type 2 error. So the power of the test is 1 minus beta. Normally, these are set by you, the researcher. So once you set alpha to be 0.05, you can also set your beta to be maybe 95%, okay, or 90%. Or you can actually calculate the power in your design as you make designs, okay? So if you have a higher power, then also the type 2 error reduces. Okay, so that is to give you a hint about the errors. We are now going to go into defining the p-value. What is a p-value? A p-value is the smallest probability where we assume the null is correct. So the p-value is also called observed significance level. So the p-value we set as researchers, it is the probability that H naught is assumed to be true. And when we reject H naught, the alpha level we've set, the significance level, is what we use to reject the null. So if our obtained probability from the data is smaller than the significance level alpha, then we reject the null hypothesis. But if we find that our probability, as we shall see in R, is bigger than 0.05, then we have no evidence to reject the null. So that is the significance level, the p-value. So we are going into t-test. The t-test is used when you have a small sample size. For example, the books say that the sample size should be less than 30. Somebody says, please recap on p-value. Okay. So we are saying the p-value is the smallest value for which the null is rejected, or it is the p-value is the probability that the null hypothesis is assumed to be true. So if we can get an example, if you're working on growth of corn and you've applied fertilizers, you are saying that you've read through literature and you've found out that if you apply nitrogen-based fertilizers, your yield is going to increase by 2%. So the null hypothesis would be that mean yield of corn is equal to maybe 20 kilograms per hectare. So the alternative would be that the mean yield is not equal to 20 kilograms per hectare. So the significance level is the probability that you assume the null is correct. So here we are going to assume that even if we are carrying out this study, our mean yield for this particular study is going to be equal to 20 kilograms per hectare. So until you collect the data after the end of the season, you harvest your yield, measure it, and then test it against the target value. That is the value which has been reported in literature, the one you're using in your null hypothesis. You either get it from literature, and if you don't have, normally we put as 0, okay? So that is the p-value. And how do we make conclusions then? If we find that the calculated p-value, the one you get from your data, as we shall see, is bigger than the significance level, then we have no evidence to reject the null. In a layman's language, the p-value of 5%, that is the probability that the mean yield of corn is 20 kilograms per hectare. Now, if the probability goes up, meaning the chances that the mean yield is equal to 20 kilograms has increased. So you have no evidence to reject the null. Now, if the probability decreases, we get a probability of 0.01, meaning the chances that the null is correct has reduced. So we have evidence to reject the null and conclude that the mean yield for corn is less than 20 kilograms per hectare. Is that okay with the p-value? Can I see in the chat people saying either no or yes? Somebody is saying that I'll show you. Okay. Okay. Okay, thank you so much. Let's go to the next slide. We are going to do this practically, so we will get more when we go to the practicals. Okay, so we are going to look at the student t-distribution. This t-test has a history. The person who invented the t-test was a student, and by then they would not allow students to publish. So he couldn't use his name, he used student. So now they didn't know which student was publishing. I don't know for what reason. Now they allow students to publish or even co-publish with their supervisors. So that is the t-distribution. So it is used when your sample size is small. And this is what happens in nature. Reason is resources. Sometimes your resources are minimal and you collect only less than 30 observations. Does it mean that you don't do some inferential statistics? No, we can use a t-test. Now, t-test follow a t-distribution, as we shall see. We have 3 types of t-test. We have a 1-sample t-test, a 2-sample t-test, and a paired sample t-test. Each of those t-tests have assumptions, as we shall see. So 1-sample t-test. So it is only used if n is small and it comes from a normal population. And also we do not know the population standard deviation. So the assumptions that the population is normally distributed, we know that when we have a histogram which is bell-shaped, then that is normal distribution. And we can now apply our t-test. But in addition to that, the sample size has to be smaller than 30 And also the population standard deviation is unknown, meaning that we are going to estimate it using the sample data. So we use the sample data to estimate the population standard deviation. So those are assumptions under the one sample t-test. Now, the t-distribution has properties. It follows n-1 degrees of freedom. You'll ask me why n-1. As we go on, we'll see, but one parameter is calculated when we are calculating the t-distribution, that is the mean. So that information that is used to calculate the mean is what we subtract from the total observation, giving us n-1 degrees of freedom, meaning that you have n-1 information to calculate the t value. So, like the normal distribution, the t-distribution has a symmetric mound, but which is flat. So it also is symmetrical, meaning the left side is equal to the right side, but it is more flat than being picked. The distribution depends on degrees of freedom. However, as the sample size increases, the t-distribution converges to the normal distribution, which is z distribution. Okay? So as the sample size becomes larger, the t-distribution converges to z, which is called the standard normal distribution. We also look for the values, the t-values from the critical values from the probability table, as we shall see. Okay? So here we are. So how do we state the hypothesis under one sample t-test? Our null hypothesis is that the mu, as you see, some people are saying that I should show you. Maybe I should stand up and show you. Okay. Is it too bright? Can you see the whiteboard? Can I have some people say yes or no? Can you see the whiteboard? This is the whiteboard, and I'm going to write here. So if you can see the whiteboard, go into the chat and say yes, yes, yes. Okay, so we are saying, somebody said I should write. Yes, let me try to write something. So we are saying that, I was saying that the normal distribution has a picked graph. Maybe that is lower, let me low. Okay. Okay. So can you now see properly? So the normal distribution, as I said, is picked and bell-shaped. Now the t-distribution, so this is the normal distribution. I'll call it n. Now the t-distribution is more round, so it can go like that, but also has a bell-shaped, meaning that when we draw a line in between, this side is equal to this side. I'm not good at drawing, so bear with my graphs. Okay, now we want to talk about the two-sided and one-sided before I show you anything. So we are saying that H naught mu is equal to mu naught. Now mu naught is a target value. a target value coming from literature, okay? Mu naught is a target value that you obtain from literature. For example, if you are assessing water quality and you know that the last 5 years the water quality has stayed at maybe 20 milliliter per something, okay? So that means this mu naught is going to be replaced with 20, which you obtain from literature. If we do not have, then we are going to use 0. Now, the alternative, I said, it can be two-sided, meaning you do not know the direction, you don't know whether it's increasing or decreasing, or one-sided. Mu is less than mu naught, meaning you know that the water quality has been decreasing. Or if you know that the water quality has been increasing, improving with time, then our mu will be greater than mu naught. Okay, so that is what we do when we are stating our hypothesis. When you've read literature and you're well versed with the biological system, you're able to state your hypothesis in terms of what is happening. Okay, so that is what I wanted to show you. And also what I want to show you is the rejection region before I get off from the whiteboard. Now, we can reject the null hypothesis using the p-value. So the p-value that we get from our data, I'm going to call it PC. If it's less than alpha, which alpha is 0.05, then we reject H naught. Okay? So if the p-value from your data is less than alpha, then we reject H naught. Otherwise, we have no evidence to reject the null. Now, I want also to show you the rejection region before I get out of here. So I'm going to draw the graph again. And this is our mean 0. And we have from here to here, we have our sigma, which is the standard deviation, and also on this side. Okay? So these are the tails. And here we have a t value, t alpha, for the single tail, for one tail. You have one tail if you know the direction again. If you know the direction, for example, if it's on the right-hand side, that means mu, your alternative hypothesis is mu is greater than mu naught. Then your tail is going to be on the right-hand side. Now, if you know that the population mean has been decreasing and you state a one-sided alternative where you're saying mu is less than mu naught, your tail is going to be on the left side. So if you're not using probabilities and you're using t values from the t distribution table, if the calculated t value falls in the rejection region here, this region where I've put some marks, is it clear? This region in the marks, if your calculated t value, I'm going to call it TC. If it falls in the rejection region, we have evidence to reject the null. Now here I'm using t distribution values, okay? And the same applies to the left-hand side. Now, assuming that our alternative hypothesis is not equal, we have a not equal sign, not this one again. So we are going to have mu is not equal to mu naught. That means all the tails are going to be occupied. We are going to have two tails. You can use the left side or the right side. So this side is going to be negative and this is going to be positive. So irrespective of the sign, negative or positive, you get the same conclusion. So if the t value falls in this region here, we reject the null. And if the t value falls in this region, we also reject the null hypothesis. So that is a simple demonstration of how we do rejection and make conclusions when we are doing a t-test. So we are going to use the same principle when we have a one sample t-test, when you have two sample t-test and paired t-test, okay? So somebody say, can you explain with examples? Yes, when we come to do the R, then we can be able to see that properly, okay? Okay, so I am moving away from the whiteboard. Somebody is saying, can I elaborate more on the error type? Okay, so we are going to go backwards, error type. So we say that alpha is the significance level. Is it visible? Significance level, and normally set at 0.05 or 5%. So this is the type 1 error. Okay? Then beta is the type 2 error. Okay? So here, you fail to reject H naught for beta type 2 error when it is actually false. Here, you reject H naught type 1 error when actually H naught is correct. And I say that to avoid these two types of error, for this one here, we increase the sample size. So make sure N is large. So if you have enough resources, make sure you have at least, if it's an experiment, maybe 30, greater than 30. If it's a survey, your N should be, for a PhD, you should have like 500 households. And if it's a master's, maybe 300. 300, and there's a formula for calculating the sample size. Okay? So when you increase N, that means the chance that you will make these two errors, these two, you will commit them reduces as the sample size increases, because then the information you're going to get, the conclusion are based on sound information, enough information. But when you have a small sample size, then you are likely to commit a type 2 error. Now for type 1 error, I said we reduce it when we set a small significance level, okay? Okay, so we are going to do the practical of R, and that is going to help us understand more. Okay, we are going to do the practical. And then let me see this question here. What if you increase the sample size, but it is okay? So what I'm saying is that once the sample size is big enough, the chances of committing type 2 error reduces. And when your alpha significance level is small, for example, 0.05, then also your chances of committing type 1 error reduces. So sometimes people want to, like you set up your alpha to be 5% originally in your proposal, but when you do your analysis, you find your data is not significant and you want it to be significant, so you change goalposts and then use 10%. Now you know the type of error you're committing, because you do not want to reject H naught, yet H naught is false. So when you state in your proposal that you're using 5% and you find your results are non-significant, don't reject the results. Non-significant results are as good as significant results. For example, when I was doing my PhD many years ago, I found that I was developing allometric equations. And I found out that for conical trees, for example, eucalyptus, height explains more of the biomass than diameter. Because conical trees, they are tall and with a smaller diameter. So you find that height is explaining more biomass in conical trees, Eucalyptus, Cupressus lustanica, compared to trees like Myzopsis eminei, whereby they grow in diameter. So in trees like the ones that grow in diameter, diameter was significant, but height was not significant. So I had to explain and go deep into the biology of trees to know why I'm getting a significant result. So a significant result is as good as a non-significant result. So when you don't change goalposts and you go to use a bigger alpha, okay, I mentioned that it has been researched and it is in literature that most of the environment, most of the sciences like forestry, agriculture, use a p-value of 0.05. Now, depending on the sensitivity of your research, if you're doing medicine, you cannot use 5% because you're dealing with the life of human beings. So you have to reduce your 5%. P-value, in other words, means the amount of error you're making in your conclusions. So if you're going to, for example, out of 100, if we multiply by 0.05, I think we get like 5 people. So if you come up with a drug and you're saying that this drug, when it's given to human beings, they will heal, and you use a 5%, meaning that on the other hand, 5 people are not going to be cured. So 5 people is a big number. How about if you have 1 million people? The number keeps on increasing. So that is the significance of a p-value. So you set a p-value depending on the sensitivity of your research. So if you set a small p-value for human and veterinary medicine, you're saving life. Okay? So always note that a p-value is the amount of error you're making in your conclusions. So when you say that you're 95% confident that something has happened, then on the other hand, you're saying that actually I'm 5% not confident that something has happened. Okay, so always remember that. Okay, so let's go back to sharing so that I can finish our theory. Okay, so this is what I've been explaining, that the null, this, as you see them here, they are called statistical hypotheses. For your research, make sure you use words. Don't state them the way they are and you say that this professor here who taught us say that we should say mu is equal to mu naught. It's because now I'm teaching statistics that I'm talking like that. But in terms of research, our null hypothesis would be either the population mean height of human beings in a certain region in Benin is maybe 2 feet, something like that. This is just an example, okay? Don't misquote me. Something like that. So you have to state the hypothesis in terms of your research. So here you can see that the alternative hypothesis, we have the one-sided, which are called one-tailed t-test. Mu is greater than mu naught, or mu is less than mu naught. And the one where we are not sure of the direction of research, we say mu is not equal to mu naught. Or in other words, there are no differences in the mean of 2 groups of people, or 2 varieties, or among the groups that you're investigating. Now, the critical values can only be obtained if you have a t-distribution table. For these notes I've included, in case you are reading, you can always refer to the t-distribution table, but we are going to use R, and it's going to calculate the t-values for us and also show us the p-values. Now, the test statistic you use, if you want to see the formula, I was telling you that we calculate the mean, and that's why we subtract 1 degree of freedom here. So you can see we have to calculate the sample mean, and we have to have a target mean over the standard error of the mean in order to get the t-value. So this quotient here, the down part, the denominator is the standard error of x bar. S is the standard deviation. N is the sample size. Mu is the population mean from literature. X bar is the sample mean. Okay, and this follows a t-distribution with n-1 degrees of freedom. Okay. Okay, so we have an example. I'm going to give an example. In this example, we have data from an experimenter. This researcher was investigating the amount of soil organic carbon stored in an agroforestry system. So he took a baseline study where he went in, measured the carbon before planting the maize under the trees, and then investigating carbon after planting maize for several seasons. So we are going to look at one season. Standard deviation. Standard deviation is the difference between the mean and the observed value. So the squared difference. So you know that the formula for standard deviation is S is equal to sigma into X. X are the observed values minus X bar squared over n-1. So the difference between the mean and the observed value is what we call standard deviation. So it measures variability. How far are the observed values from the mean of the population? That is standard deviation. Standard error measures precision. How precise is the value of the mean? That is the standard error. Okay, and normally when we are constructing error bars, I know you people like error bars, we use either the standard deviation or the standard error. If you use the standard error, you're actually computing the confidence interval. The error bars will be representing the confidence interval, as we shall see. Okay, any other question? Okay, so let's see. So I want us to go through the theory for all of the types of t-test. Then afterwards we go to R and do the practicals bit by bit, as I'll be explaining, so that we don't move back and forth, okay? So I'm assuming that you will remember some theory which you've already done now, and then when we are doing R, you can put the two together, and then you're good to go. So we have the two independent sample t-test. And when we have two samples, we have two scenarios. If we have two groups of people receiving the same treatment, then we can use two independent sample t-test. If we have one group of people receiving the same treatment, but measured over 2 periods, before and after, then we can use a paired t-test. So let me repeat. So using the example of soil organic carbon, the researcher went in and measured the baseline, the existing soil organic carbon. Then if he goes back to the same plots, and assuming that he marks them, goes back to the same plots after planting and measures soil organic carbon, that means that the baseline information is correlated to the information after planting. And in that case, we use a paired t-test. Now, if he goes and does a baseline study and afterwards doesn't mark the plots, but goes in again and picks in other areas and picks soils, then that means that the two samples are independent and we can use a two sample independent t-test. Let me give another example for paired. Assuming we have a plant The plant produces seeds both on top and the bottom. And the stem part has also seed or fruit, and even the top has fruit. So we want to know the yield of the plant over time, or we want just to know the yield at one point in time. So we measure the number of fruits on top and the number of fruits on bottom. But it is the same tree. And assuming you have 10 trees and you're doing the same, you're measuring top, bottom, meaning that the information you get above is correlated to the information you get below. And in that case, we use a pair t-test because there is dependence. This tree which you're measuring, the same biological functions happening the bottom are also happening on the top. So that is the correlation we are talking about. There is dependence in the information, and we can only use a pair t-test to test that the differences in weights of the two fruits. Okay, so let me go to something else. The two sample independent t-test. The samples have to be independent. Two groups of people subjected to similar treatment. Those are independent. Then we can use a two independent t-test. And if it is a t-test, the samples have to be less than 30, according to literature. They are randomly selected, meaning that the two groups you randomly select and then apply your treatment. Now, we also assume that the variances are equal for the two groups. Okay? So this is an assumption normally we make, but all statistical packages help you to either use this variance or not to use the assumption. So if we assume that the variance of group 1 is equal to group 2, we can actually test and find out whether that is true. And we are going to look at that in R. So under the two independent sample t-test, the principles still remain the same as in the one sample t-test. You can see mu1 minus mu2, meaning group 1, the mean of group 1 minus the mean of group 2 is equal to the difference, which is the target difference in literature. We can also have a one-sided and two-sided where we do not know about the literature. The one-sided are called one-tailed test. The two-sided is called two-tailed test. And when you are testing at alpha of 0.05, at one-tailed, our alpha is going to remain 0.05. For two-tailed, our alpha is going to be divided by 2 because you have two sides, okay? So it is going to be 0.025. So the two-tailed becomes more powerful because you're testing at a smaller p-value compared to the one-tailed test. So if you're still not understanding what I'm saying that we've set our significance level at 5%, and when we perform a one-tailed test where we know the direction that the difference in the two groups of the mean is greater than or less than the difference stated in literature, then that becomes a one-tailed test and our alpha is 0.05. That is the significance level. Now, still using the same significance level of 0.05, but we do not know the direction of research. So we are not sure of what is happening in the biological system. We are just going to say that the population mean growth of group 1 is different from the population mean growth of group 2. And that means that because we are going to look into the two tails, our alpha is going to be divided by 2, meaning that you will be comparing your results at 0.025. So even in R, once you state that your null hypothesis is a two-tailed, automatically you're going to test at 0.025. When you say it's one-tailed, you will test at 5%. Okay? Okay, we talked about rejection region. You remember the rejection region. So this is for you to read. So I'll move out of that. And then we have the function in R that we use to conduct a t-test. The function in R that we use is called t.t-test. Okay? And in order to get your t.test in R, you must have put in the library. And that library is called dplyr. But we are going to load all the libraries that are shown in the script, and then we perform our t-test. You can see that in this script that I've noted, it is saying t.test xy. So this is a two sample t-test. You can see it has group X and group Y is equal to null. And then alternative, you can choose. Okay? Either two-sided, less or greater than. So you can choose one of the two. And then mu is equal to 0. Then they're asking you, is it a paired t-test? You say false because you want to conduct a two-sample t-test. And is the variance equal? You say false because you haven't tested. Now, if you say true, then it's going to calculate using variance equal. If you say false, it's not going to assume variance is equal. Confidence level is equal to 0.955. Confidence level is 0.955 because your alpha has been set to 0.05. Okay. Pair t-test. Or do we have any question? Any question? Okay. So let's go ahead, pair t-test. As I gave you an example, the data we are going to use is within one plant, the seed was collected on the top of the tree and the bottom part. So we had 13 trees and we are collecting information, the weight of seed on bottom, weight of seed on top. And we want to compare, is the bottom giving us better weight compared to the top? So in that case, because we are collecting from the same experimental unit, the data is correlated. And because it is correlated, we use a paired sample t-test. Under paired sample t-test, we actually get the differences. You can see the parameter of interest is mu minus mu naught. You get the differences, then you deal with the differences. You test the differences, okay? So assumptions here is that the distributions have to still be normally distributed. The samples have to be small. You have to have conducted random selection. The samples are not independent. They are paired. They are dependent on each other. For you to perform a paired t-test, the samples have to be dependent. Okay? And so what we do in a paired t-test, we actually get the differences between the two occasions, bottom and top, and then conduct a t-test on the differences. So the same principle we were using for stating the hypothesis is still the same. You can see that here we are using mu d, meaning the mean difference. Okay? So we subtracted the group 1 minus group 2, meaning top minus bottom is equal to d naught, and d naught is a target value from literature. If we do not have it, we use 0. We normally put 0, or the computer puts 0 automatically, or you can actually put the target value that you've read in literature. Okay, and then we have the one-sided t-test or one-tailed t-test and two-tailed t-test. And the t-distribution, the t-test is going to be the mean difference minus the d naught, which is the target value, over the standard error of the difference. So again, rejection, we use the same principles. Okay. Okay, let's go to R, unless if you have questions before we go to R and make things more practical and very interesting. Okay. So do you have any question? Any question? Q&A. What? Okay, I have a question here. More clarity. When do we use one sample t-test? Somebody says I should go back to slide number second last. Okay, when do we use the one sample t-test? When you have only one variable that you want to test or one population that you want to look at, then we use the one sample t-test. And the sample size has to be small. Data comes from a normal distribution. That's when we can use a one sample t-test. And I've said for paired t-test, the data is correlated, depends on the other. For example, you've measured before and after on the same plots, then that data is correlated. For example, you go to monitor water infiltration rates after a shower, maybe after season, you're looking at how water penetrates the soil over time. So even that, the data you get over time is correlated. So if you have 2 time points, then you need to use a paired t-test, not a 2 sample t-test, because of that correlation, okay? So here somebody says I should re-explain this last slide. It is stating how we state the hypothesis, and I'm saying that here we have mu1 minus mu2 is equal to d naught, where d naught is the target difference. Mu1, for example, is the seeds collected on top and also the average seeds collected on bottom for the same tree. And then we are comparing them by looking at the target value from literature. If we do not have the target value, we use 0. And the alternative hypothesis can either be stated as mu1 minus mu2 is greater than d naught or less than d naught, which is a one-tailed t-test. And if you do not know the direction of your research, then it is a two-tailed t-test. So in terms of the example we are going to use, we can say that the average weight of the seeds at the bottom is different from the average seed at the top. That is for the two-tailed test. I don't understand that question. Is it true because a scenario of research question is more in descriptive studies? No, the last one. Okay. I'm measuring the light. Okay, sorry about that. I'm looking at the question on the Q&A, and it's saying I'm measuring light penetration at 3 levels in shaded coffee, the top of coffee tree, the middle part of the tree, and the downer part. Are these data correlated? Yes, a big yes. Capital yes. The data is correlated. And if you have 3 of them, you can't even use the paired t-test, but now you have to use repeated measurements analysis, okay? So for that person who brought the question where he's measuring light penetration on the top of the tree, in the middle, and the bottom, all those results are correlated, okay? So in that case, because now the groups are more than 2, we use repeated measurement ANOVA. Okay, so you go and read about repeated measurement ANOVA, or we will look at it when we are looking at analysis of variance. Okay, so we are going to R. So where is the question? Q&A. Okay, there are some questions in the Q&A, so let me attend to them before we go to R. Kindly repeat slide number 16 about the function for t.t test. We are going to look at that in R. So that is okay. We will look at it, but thank you for the comment. Okay. We will look at it, Musa. We are going to look at it in R. Okay. So there we go. So we are going to R, and I've already sent you the script. It is called Pvalue 0. So let's go to R. I'm going to stop sharing and share R. So as you also go to your R on your laptops, your desktop, your notepad, whichever you're using. Yes, Jean, we can compare two means from two different samples. It also depends on your design, but we can compare two means from two different samples. So long as what you measured on sample A is what we measured on sample B. Okay. For example, if we have two varieties of corn and we are looking at yield and we've applied fertilizer to them, then we are measuring yield in variety A and yield in variety B. We can compare the two using a two sample t-test. Okay. Okay, so we are in R and we have this follow-up note which I sent last evening. The first thing we are going to do is we are going to, okay, let me remove this. So it says zoom out, like that. Okay. So I hope now it's clear. We are going to use this script to run our t-test. We need to run these libraries, so you just load them. So highlight and load the library. We are going to work together. Make sure you have your R open, and I am going to run everything. I know you'll ask me, do we need all of this? But let's just run them. It doesn't cost you anything. So run, you see this green button here, run the current line, which is selected. So you run and it is running. Then afterwards, we are going to set the directorate where our data is. So you're going to navigate where you stored your data. So if you do not want to write the command, I know you would be happy to do Windows in R. So we are going to use session, set working directorate. I'm right there. I'm going to pause. You go to session on your menu under R Studio. So once you download R and R Studio, you open R Studio, it will bring in the consoler for R. So you don't need to open R separately from R Studio. So once you have them on the laptop, just open R Studio and we will be able to do all the analysis. Okay, so now go to session, set working directorate. I am moving to choose directorate. There I am. So can we go on? So put a yes in the chat so that we can go on. Is that okay? Okay, then click choose directorate, click choose directorate. When you click choose directorate, it takes you to where you store your information. So you will go and browse where your R information is, where you've been storing the. Okay, so let me go back. Somebody says we go slow. Okay, so to set our directorate, instead of writing the command, I'm going to use session. in your script, somebody says I should repeat loading library. In your script, you can see it is still highlighted in blue. Just highlight, select all of them and click run. Run is at the bottom, the fourth row. On RStudio, there is this green button. If you point at it, it says run, selected or current line. So once you run, it is going to load all of them, okay, in that script. Once you've received the script, you just need actually to open the script and it will directly open in RStudio. And then you go and highlight all those words you see with the library, highlight them and click run. Once you're there, we are going to set our directorate so that when we are writing our commands, all our information will be sent to the directorate we've told the computer to use. And also when you call your data, it will know where you stored the data. So where you have stored the data that I sent is where we are going to set directorate as our directorate to use. So we go to session, set working directorate. I'm pausing and choose working directorate. There I am, you can see. I believe it's more visible. Session, set working directorate and choose directorate. So are we there? Can we see a yes in the chat so that I move on? Okay, so we are good to go. Okay, thank you very much. So let's now click. Okay, thank you. Excellent. Choose directorate. Click, choose directorate. Just click with your mouse. You click, choose directorate. So when you click choose directorate, I'm going to move the dialog box. You can see the one which is moving. So you browse to where your data is. So my data, if I go to documents, you can see I have so many things on my laptop. I'm going to look for R package, and under R package, I look for follow-up. So my directorate is called follow-up. That's where my data is. Once you do that, click open. Do that. If we look at the console down here, you will see set working directorate and the root. Okay? So you will see it here, right here. I am highlighting it with blue. So you've already set your working directorate. So have you all set your working directorate? Can I see yes? Because if you've not set, you'll not be able to follow. Okay? Okay, thank you. Excellent. Now, we are going to read our data. Next step. As I've told you, the history behind this data is that the researcher was investigating soil organic carbon in an agroforestry system, and the site where he wanted to investigate, the trees were already existing. They were around 11 years old. So he went in and measured soil organic carbon before planting, and then after planting, he established plots and planted corn to make it an agroforestry system, then observed for 2 seasons, and then for each season he measured the soil organic carbon. Now for this data, we have only data for 1 season, and the data is truncated. It's not all the data because we are not given the permission to use all the data. So it is truncated. Okay? So let's read the data. So for you to read the data, you can type carbon. Carbon is the object you want to assign to your data, and then you put this less than sign read.csv. Then in bracket, we are going to put the file, the CSV file, carbon in quotes. So let's run that. Just place your cursor anywhere in that line and run. When you run and you're not getting any comment, that means you're good to go. And the function head prints your data. So let's run the second command, which says head. So you click that, you see our data. So we are able to observe our data. So I'm here trying to show you the data. You can see in the console, the data has been printed. It has plot number, it has carbon BP, which means baseline, or before planting, then carbon after harvesting. Okay. So after bringing in our data, it's always good practice to do summaries. Yesterday, I saw that my colleague, Dr. Helen, taught you how to do some summaries. So those ones you can do in your free time. We can actually do them here. We can just type summary. You know, if you want to play with your data and find out whether it is good data or there are differences, we can just type summary. You see? And remember, the file now you're dealing with is called carbon, because you told R that you're going to read your CVS file and call it carbon. So that's why I'm saying summarize carbon. Summarize meaning it's going to give you descriptive stat. So then when I run, I get some magic happening here. I get the minimum carbon. It has summarized everything from even the plot number to baseline carbon and after harvesting. So we see the minimum carbon was 16.74 kilogram per plot, and the minimum under after is 12.69. The first quartile is 20, the minimum is 22.12 before planting, and after planting it is 21.9. You can see that the carbon decreased, which is reasonable because you opened up the ground and it had to escape. That's why you see the values are decreasing. So that is the summary. You can see that there are differences in the mean values, and you want to find out whether those are significant. But for our sample t-test, we are only going to look at carbon before planting. That is BP. Okay. Any question before we go on? Error, cannot open the connection. In addition, warning, cannot open carbon. Oh, your carbon file, you see you've written a capital C. Who is this one? Let me see the name of the person. Make sure the name of the carbon file is with the lowercase. R is case sensitive. So when you change to lowercase, then it is going to work. Okay? Let me see another problem here. Yes, recap. Would you please repeat once more? I don't even know where to start from. Where should I start from? Give me a hint. Somebody is saying is using R Studio 4.05 and it's not letting you to download. You will do that in the free time. Please try to update your R using the tools command from it. You will see update R Studio. Okay, so I start from where I input data and also summaries. Okay, let me go back from reading the data. So I'm going to highlight the command which reads the data in. That is the one highlighted in blue. Can you all see it? So the first word, which is carbon, I'm assigning an object called carbon to my command read so that it reads that file which I sent to you called carbon and reads it into R. So when I'm working with the file called carbon CSV, it has been renamed carbon. That is the object carbon, okay? So for me to read it from where it has been stored, I say carbon. You can actually use equal sign, or you can use that less than sign, read.csv. Then in quotes, I put in the CVS file, which you downloaded from the notes. Now remember, if you've not set the working directorate, you are also going to get an error. Okay? So apart from writing carbon with the uppercase, if you've not set your working directorate where that data is, R is not going to see the data. Please make sure you set directorate to where you downloaded and saved all the documents we sent. Okay, so if that is clear, I am going to run it again. There we go. Then head carbon is for you to print your data set so that you can see it. And then I said, for every data set, we need to do a summary. Okay? And look at the means. We want to look at the standard deviations of the data we have. So we can use summary statistics to give you some numerical summaries, or you can actually construct a plot. Okay, so I am going to use summary. You can see, I'm going to highlight it in blue. That is summary. And carbon is the object that I use to name and call the data from where I'd stored it. So this carbon here has my data now. So I say summary, carbon. Then I run. I'm running the blue selection. So when I run, I get an output in the console in the lower left bottom window. There's what we call a console. So it has an output. It has the mean, first quarter, median, mean. Before I explain, do everybody has or have the means? Okay. Okay, so you all have the printout for the mean, the summary statistics, okay. Okay, so let's go ahead and interpret the output. So we looked at the minimum value. Let's go straight to carbon underscore BP. That is carbon before planting. The minimum, that is the lowest soil organic carbon, was 16.7 kilograms per plot. The first quartile has 20.87. The median has 21.73, and the mean had 22.12. The maximum organic carbon before planting was 28.6. Now, if we go to this other variable of after planting, we see the mean is 12.69, meaning that there was a decrease in soil organic carbon. Reason biologically, once you open up the ground, it is going to evaporate in form of carbon dioxide. So that is what happened in this system. The first quartile for after planting is 20.22. The median, almost not so much different, and the mean is 21.9. The maximum value is 26.61. Okay? So that is the result we got from the summary. Now, we are going to conduct our one sample t-test, But we are going to look at carbon before planting only because it is called a one sample. You have only one variable. You want to look at one population. Okay? So we are going to look at carbon before planting. And afterwards, if we are looking at two sample t-tests, we look at before planting and after planting. So can we go ahead? Is there any question? Anybody with a query or a comment? Can we go ahead? Can I see some comments in the chat? Okay, let me go ahead. I have been reminded that you need a break. Do you need a break or we go ahead? Let me find out from the chat. If you need a break, somebody says, okay, go ahead, break. It will depend on how many breaks. No break, go ahead, go ahead. Okay, I'm going to be fair to everybody. Can we have a 5 minutes break? So we will be back at 13:11. 5 minutes break. And remember that they will cut us off before we finish our t-test. Yet I wanted us to finish t-test today. So 5 minutes, let me give you a break so that you can refresh, go out and stretch yourself, call somebody home. So 5 minutes, okay? Let's be back at 13:11. Go for a break. Okay, are we back? Can I see some comment in the chat? Are we back? Okay. Okay, let's go ahead. We are going to go to the one sample t-test. Let's move on. One sample t-test. So I have labeled it one sample t-test, and the function we use is called test.test. And the first part you see here is the file name, the object which I called carbon. Okay? And the $sign is telling us that we call this variable here called BP, carbon underscore BP. Mu is equal to 0 is the null hypothesis. We are saying that the mean, the population mean is equal to 0 because we do not have a target value. Otherwise, if we had a target value, we would replace 0 with either 20 or 30. Okay? So that is the command you need to do a one sample t-test. Okay, so let's run that. Put your cursor there, either end or middle, and run. So when you run, you get some good analysis here. So we are going to explain the analysis. So I'm assuming everybody has an output. So let me see in the chat that you have an output. You say yes, 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 you have an output. Because if you don't have the output, then we cannot. Somebody, Franco, you don't have an output. Jeremiah. Yeah? Oh, no, letting on. Okay. For those who don't get an output, during the support session, we will help you. So don't worry. We will go through it and you can catch up. But please pay attention to the interpretation. Okay? Okay. So you can see in the console down here, the left bottom window, it has one sample t-test. Data is carbon, and we are looking at a variable called carbon underscore BP, or baseline, or before planting. It gives us a t-value. You remember I gave you a formula. So this is the t-value which results from the mean of carbon over the standard error of carbon. The ratio between the mean of carbon and the standard error of carbon gives us a t-value of 43.56. And then we have degrees of freedom. If we get degrees of freedom of that 23, it means that the total number of observations we have are 24 data values. Because remember, the degrees of freedom is n minus 1. So our degrees of freedom are 23, meaning that the original total number of observations were 23 plus 1, making it 24. The p-value, you can see it is 2.2 times 10 to the power minus 16, meaning that this p-value is 0.000, count 16 places. Actually, count 15 up to 2. It is 0.00000, yeah? It is smaller than 0.05. If we want to write 0.05 in this term, we are going to say we are going to say actually 5 times 10 to power minus 2. Okay? So for 0.05, we have only 2 decimal places. So that's why we write 5 times 10 to the power minus 2. So that we can divide by 100 and get 0.05. Now here we are dividing, I think, with I don't know how many billions of values to get 0.000. Now, before I explain the p-value, we want to look at the alternative hypothesis. Alternative hypothesis is true mean is not equal to 0. So here, you remember our notes. We say the null hypothesis, if you don't know the direction, you just put not equal sign. So even in this case, it has just put not equal sign. The null, we've already put it in the command. Our command was mu is equal to 0. Here, the alternative, it has printed the true mean is not equal to 0. So that's what we are testing. So let's now interpret our p-value. Given that our alternative, the true mean is not equal to 0, and our null, the true mean is equal to 0, and the probability that the null is assumed to be correct is 0.05, is 5%. Now, if we get a value which is smaller than 0.05, we have evidence to reject the null and conclude that the true mean is not equal to 0. Okay? Okay? So that is the alternative hypothesis, is that the true mean is not equal to 0. The null was mu, or true mean is equal to 0. The p-value we've gotten from our data shows that the true mean is not equal to 0 because the p-value we've gotten is smaller than 0.05. We have evidence to reject the null hypothesis. Okay? So now, R gives you also the confidence interval. It gives you the confidence interval. A confidence interval is a range of values within which the mu, the true population mean, lies. Not between, within which. It is a range of possible values, the lowest and the uppermost value, or the upper limit. The lower limit and upper limit, a range of possible values within which mu lies, the true population mean lies. So here I've got a confidence interval of 21.066 as the lower value, and the upper value is 23.67. So this is the range of possible values, and it can be interpreted like, in layman's language, that when you do repeated sampling, if you go back to the field where you collect this data and do it 100 times, so you're going to collect 100 samples of soils, different sessions. You're going to go collect sample 1 of 24 observations, sample 2 of 24 observations, do the testing of soil organic carbon, then do the analysis and compute the confidence interval. You will find that 95% of all those 100 are going to include the mean value. On the other hand, we are 95% confident that the true mean lies within those two values, 21.066 and 23.167. So there are two ways you can interpret. You can either say that if I conducted my study 100 times, collected different samples of the same sample size 100 times, it implies that when I calculate the confidence intervals, 95% of them are going to include the value of the mean. Or you can say that you're 95% confident that the value of the mean, the true mean, lies within 21.06 and 23.17. I believe that is clear. Okay? And they also give you the sample mean down here, which is 22.167, which lies within this confidence interval. Any question? Let me go to the chat. Any question? You did not explain H and H naught hypothesis before running the analysis. Okay, Ernest, thank you. We reject the null? Yes, we don't accept the Okay, thank you very much. I've seen two comments. One person is saying, I didn't state the null hypothesis before I ran. Thank you for the comment. The null hypothesis is the true soil organic carbon mean or average is equal to 0, while the true soil organic carbon before planting is not equal to 0. What? The t-value. Okay, so I say that the t-value, remember the equation I gave you, The t-value is the ratio between the mean, the sample mean, and the standard error of the sample mean. With the t-value, the computer gives you corresponding degrees of freedom, which is n-1, meaning that our total observations must have been 24. Minus 1, we get 23. Then we also get a p-value. So it is that p-value now which helps us to make conclusions, whether we reject the null hypothesis or not. So in this case, our p-value is smaller than 0.05. So we have evidence to reject the null hypothesis and conclude that the true mean is actually not equal to 0. Are we together, ladies and gentlemen? Can we go to the next test before our time? Sure. Okay, so somebody says I should start with what? Summary. Okay, now, Anthony, let's go to the two sample t-test because the explanation is almost the same so that we can have opportunity to see what happens in the two sample t-test, which I want to show you. Okay, so we did our one sample t-test, and I'm going to put something to separate. So let's go to two sample t-test. So remember that in our two sample t-test, we assumed the data from the two groups is normally distributed. We also assumed that they are independent, so no correlation. We assumed that the variances of carbon before planting and after planting is equal. So among all those assumptions, all of them can be tested. Normality test is used to test whether the data is normally distributed. And if we get something close to a bell-shaped, then our data is normally distributed. And we can also test the variance assumption, which we are going to do. So for us to be able to test the variance assumption, we use this function here, var.test. var means variance. So before I do the var.test, there's a hypothesis that this test is looking at. So we said that we are assuming the variances before planting is equal to the variance after planting. That is our null hypothesis. Our alternative is that the variance before planting is different from the variance after planting. Okay, so those are the two hypotheses we are looking at. Now we are going to do our test. Now for two sample t-tests, we need two variables. So we are looking at carbon before and carbon after. In this experiment, this researcher never marked the plots where he got his carbon before. So what he did, he went in, collected the soil samples and never marked the plots. So he just went back, collected the soil samples without going to the same plots. So making these two variables independent. So that's why we can apply a two sample t-test. So before we apply the two sample t-test, let us test whether the variances are equal or not. So we can now put our cursor at the end of this command, which I'm highlighting in blue for everybody to see, and then click run. So when we click run, it gives us the F-test to compare two variances. In the consoler, look in the consoler, you will see F-test to compare two variances. The data is carbon before planting and carbon after planting. The F value is 0.714. The degrees of freedom is 23 for the numerator and denominator is 23. So when we compare two variances, we are putting the variance of before planting on top and the variance of after planting at the bottom. So we have a numerator and a denominator. The corresponding p-value I'm going to highlight in blue for you to see is 0.4258. 0.4258. Now, if we set our significance level at 5%, this case, we are saying that the chance that the null is true is actually has increased from 0.05 to 42% or 0.42. So what am I saying? That the p-value from the data is larger than 0.05, meaning we have no evidence to reject the null hypothesis. So the significance level is the probability that we assume the null is correct. And our null here is that the variance of BP is equal to the variance of A after harvesting. Now we get a p-value of 0.4258, which is actually big. It is increasing the chances of the null hypothesis being correct, meaning we have no evidence to reject the null and conclude that actually the variance of carbon BP is similar to the variance of carbon AH. So after that, we can now do our two sample t-tests because we can assume now equal variance. So how about if the p-value was smaller than 0.05? Then in that case, when we are doing our t-test, we know that we are dealing with two samples whose variances are far different from each other. We will tell R that the variances are not equal. So the way they calculate the degrees of freedom differ when variances are equal and when variances are not equal. But the results are almost similar for both scenarios. Okay, so can I see any comment in the chat? Is variance the same as F? No, F is F test, F ratio. F is an F distribution. Variance, I said, is the value which shows the spread in the observed values from the mean. So when you have a variance which is bigger than the mean, it means the data is so variable. It has a lot of noise. Okay, somebody is saying I should explain that the true ratio variance is not equal to 1. Okay. He says he's not getting when to reject and when to accept. Okay, good. So let's go back to the test. We already know how to get this test here, which I've highlighted in blue. We all know how to get it, okay? Now, we assumed that the variances in the notes which you already have, I say that one of the assumptions under the two sample independent t-test is that variances are equal. The variance of before planting is equal to the variance of after planting. We said the data should follow a normal distribution. We also say the sample size should be small. According to literature, it should be smaller than 30 for you to conduct a t-test. Now we are saying that all these assumptions can be proved. Normality test can be used to prove normal distribution. Now, for variance to be equal, we use the var.test function in R to test that if the variances are equal, even the ratio of the variance is equal to 1. So, in the null hypothesis, you can either say sigma 1 squared is equal to sigma 2 squared. Or you can say the ratio of the two variances is equal to 1. That is the null. Alternative is that the true ratio of the variances is not equal to 1. So if the ratio is not equal to 1, that means that those two variances are not equal. So the var.test helps us to find out whether that assumption is valid or not. Okay, so in var.test, it gives us an F value. The F test is a ratio of the variance for carbon before planting and carbon after planting. Now, it's looking at that ratio and calculating the corresponding p-value. The corresponding p-value for the data is 0.425. Now, I said that the null hypothesis has a probability called the significance level, which is set by the researcher. And it is the probability, the smallest probability, where we assume the null hypothesis is true. So for the null to be true, alpha, or the probability, is 0.05. So if we get from our data now, if we get a bigger probability than 0.05, that means we are increasing the chance of the null to be true. If we get a smaller p-value, 0.02, we have reduced the chance of the null to be true. So in this case, our p-value is 0.425, meaning we've increased the chance that the null is true. And we have no evidence to reject the null because we are increasing the probability that the null is correct. So in that case, we conclude that our variances are equal. We can go ahead and conduct our t-test assuming the variances are equal. Okay, so I've sorted all those people's comments in a go. Okay, so let's go now and conduct our t-test in the R script. Can we go ahead? Can I see some comments in the chat? Can we go ahead? Or you are tired after the break just broke you down? Can we go ahead? Okay, so I have two options which I have put for testing for two sample t-test. The first one assumes that the variances are equal, so I put t.test, carbon before planting, carbon after planting. I believe now you know what the $sign means. It calls the variable in the object carbon. In the file, the object carbon is where our data is. So we are calling carbon underscore BP. And even in the object carbon, we are calling carbon underscore AH. Those are the two variables we are testing. So if we run that, we get an output. Has everybody gotten an output so that we can go ahead? Have you got the output? Okay. Yes, yes. Excellent. So let's go to the interpretation. In R, the two samples t-test is called Welch two-sample t-test. In other packages, it's called the student t-test, or it is called two-sample independent t-test. Okay, they are all the same. If you know how to use SPSS or GeneStart or SAS, you can test and see whether the results you're getting in R are the same, and then you'll be able to confirm that what you're doing in R is okay. So here, the first line is showing you the data you're testing. I'm highlighting it in blue. The second line shows you the t-value, the degrees of freedom, and the p-value. The hypothesis we are testing here is that the average soil organic carbon before planting is the same as the average soil organic carbon after planting. The alternative is that there is no difference in the average carbon before planting and average carbon after planting. I'm going to repeat. The null hypothesis is that there is no difference in the average carbon before planting and after planting. And the null is that there is a difference in the average soil organic carbon before planting and after planting. So I've highlighted the results in blue. When you're presenting in your paper, that is the bit you collect. You pick that bit which I've highlighted in blue and paste it in your document. You paste the t-value, the degrees of freedom, and the p-value. Some people are used to saying p is less than or p greater than. In the recent past, journals want you to state the real correct p-value. So it's better you put the real p-value. P is equal to 0.7954. Okay, so let's interpret the values. So here we've assumed that our variances are equal and our t-value is 0.26, degrees of freedom 44, p-value is 0.7957. So we were testing it at a significance level of 0.05. 0.05 is the probability that we are assuming that the average carbon for before planting is equal to the average carbon for after planting. So if we get a bigger p-value, it means that the chances that the null hypothesis is true has increased. So we have no evidence to reject the null. In layman's language, the p-value of 0.7954 is greater than 0.05, meaning we have no evidence to reject the null hypothesis and conclude that there is no difference. We don't see a difference between the soil carbon before planting and after planting. Okay? Let me see in the chart. Why is the degrees of freedom with a fraction? Okay, I can explain. Very okay. Okay. Okay, so I'm first going to run the next part, then I explain why we have degrees of freedom of 44.75. So below this analysis, we also have a confidence interval, okay? If you look at the 95% confidence interval, I have highlighted in blue. It ranges from minus 1.379 to positive 1.789. It implies that one of the possible values of the average mean difference is 0. So if one of the possible values is 0, that is also one way of telling you that actually the mean difference between PB carbon and carbon AA is equal to 0 because one of its possible values is 0. So if you look at the confidence interval, if you draw a number line, we used to draw a number line in grade 2, you will see that 0 is one of the possible values of the mean difference. And we are testing the mean difference, whether it is different from 0. So here it is telling us that actually the mean difference is equal to 0. meaning there are no differences between the carbon before planting and carbon after planting. So below here we have the means for both. You can see one is 22, that is before planting, after planting, it's 21. So here, when it comes to these estimates, for it to make sense, you need to go and read about carbon sequestration and see why there was no difference when you planted the corn after opening up the ground. You will see that it is likely true that the soil organic carbon decreased because you opened up the ground and what had been stored evaporated in form of carbon dioxide. So now you're writing your results and discussing them, and then you quote where that person quoted that once you open up the ground, which has stayed for some time without being tilled, you will expose the ground to the sun, and because of the biological reactions which I won't explain here, the carbon is converted into carbon dioxide and it reduces the baseline carbon to what we see in this data. Okay? Okay, let me see in the chat. Huh? If the p-value was smaller, we are going to see that in the, we are going to see in the, to see those results which are significant, but if the p-value is smaller than 0.05, we reject the null hypothesis. And so we reject the null if our p-value here is smaller, meaning that it should be smaller than this value, like 0.02 or 0.01 or 0.000, then we reject the null. But if it's bigger than 0.05, then we have no evidence to reject the null, or we fail to reject the null. Okay, so that those are the two things. Okay, so I wanted to run something. Yes, I'm going to explain. So the next alternative here, remember here we didn't have any options. So here in the test.test, we have the same command as before, but we are saying alternative is two-sided, mu is equal to 0, and then we are also saying variance is equal is true, because we've already tested it. So in this second line, we are being more specific than the first line. In the is equal, we have a confidence level of 0.97. The null hypothesis is mu is equal to 0, and we have a two-sided alternative. So let's run the whole of this and see what happens. Okay, so before I explain the results, you can see that the difference between the first line and the second line is that when we tell R that the variance is equal, it is true, then the degrees of freedom are not going to have decimal places. In the first case, we didn't specify that variance was equal, so it assumed that we are not using that assumption of equality. So that's why the degrees had decimal places. When we assume the variances are equal, the degrees of freedom is going to be N1 plus N2 minus 2. So N1 is 24, N2 is 24, that is 48 minus 2 gives you 46. This occurs only when we tell our variance is equal, because we've already tested that. In the first scenario here, if we look at the results here, you can see degrees of freedom has 44.756 because R knows that because you didn't tell it that the variances were equal, it assumed variances were not equal. Okay, then that's why it is 6. So that is what I wanted to clarify. Okay, so here we've now clarified it by being specific in the command, telling R that we have these two variables, BP and AH, carbon. The alternative is two-sided, mu is equal to 0, it is not a paired t-test, and the variances are equal. Is it true? So if you put false here, where I see my highlight, if we see var dot equal equals false, meaning we are telling R that the variances are not equal. So you calculate your t value with adjusting for degrees of freedom. Okay, so I hope that is clear. So we can now interpret. We are left with a few minutes to go. And before I interpret the results, I have sent you an assignment, which I want you to attempt. Maybe I put up the assignment. I sent the assignment this morning for you. Please do. Dr. Helen is going to paste it in the chat. But in the meantime, pay attention to the interpretation. You can see the only difference is the degrees of freedom. The p-value is still bigger than 0.05, meaning that we have no evidence to reject the null hypothesis and conclude that the soil organic carbon before planting is not different from the soil organic carbon after planting. The 95% confidence interval still has, it ranges from positive to negative to positive. As I said, it includes 0, meaning that our result here is true that there are no differences, because one of the possible value of the difference between carbon before planting and carbon after planting is 0. So after getting these results, you can take them to your document, but now read the biology behind carbon sequestration, and you'll be able now to interpret the results and make sure that when you read somebody's paper, you cite them. Otherwise, you'll be caught for having plagiarized. Okay. Okay, so test. Tomorrow we will do a recap and make sure you do the assignment. I have sent you one data set, whether you've understood or you need some more talking about t-test. Then I'm going to send more information about analysis of variance for tomorrow's session. Okay? Otherwise, if there are no more queries or comments, yes, we recommend that you do the equality test of variance before you do the t-test. Somebody is asking, so do you recommend that we do the equality test before doing the two-sample t-test? Yes, do the equality test before you do the two-sample t-test. I have sent the data set. The data set is there. If it's not there, it is within the assignment. You can enter it into Excel, save it as a CVS file, then open it in R. That will be a good exercise for you if I've forgotten to send you the data set. Okay? If we have more than 2 samples, we use analysis of variance, which we are going to look at tomorrow. Okay, I am going to send out a support link. Have you formulated one? Okay, let me try to formulate. I'm going to go off and formulate the support link so that I can send it to you before you go. So please wait before you go. So I'll stop this. David, please don't switch off. Give us 2 minutes. I formulate. Can we use the same? No. Not yet. The internet is slow. You can formulate if you can in your email. Internet too slow.
Next time should I put?
Put 2. Okay, it has come. 2 o'clock. 45 minutes. Today is 2. Recurring. Okay, 7 occurrences. I've formulated also, so in case you don't save. Okay. Wait. Huh? Can I send mine now? Copy invitation. I copied everything. Okay, ladies and gentlemen, here is the support link. For those who are interested in the support, it is right there. I have sent it. Let me put it in the Q&A. So it is the same link we are going to use. Okay. Assignment will present it in class. So I've sent you the support link. It starts at 2. So we have 4 minutes only, and it's only for 45 minutes. You are welcome to join the support after this session. So this session is ending as soon as the IT person closes. So tomorrow we'll do a recap. Make sure you do that exercise to see whether you are understanding or you're following, and you can apply it to your data. Okay, thank you very much. See you in the support session. And Okay, the recordings are being developed. Somebody else is developing the recordings and will send them. I believe before the 6 days end, you'll have the recording. You can't see the link. Okay, here it is. I have sent the link. Second time. Okay. Okay, see you then. Bye. So hopefully, oh, somebody says they can't see the link. There it is. Okay.